Welcome to Chemical Equilibrium. So let's start out by talking about the equilibrium constant. Now, for a generic equilibrium reaction, which we're going to write this way, where we have A plus B going to C plus D, and then of course we've got our coefficients that we're going to label with a lowercase a, b, lowercase c, and d. We can then write our equilibrium constant, capital K. Remember, capital K is an equilibrium constant, lowercase k denotes a rate constant. So K is equal to the concentration of product C raised to the C power times the concentration of product D raised to the D power divided by the concentration of A raised to the A power times the concentration of B raised to the B power. That is, we've got products raised to their coefficients in the balanced reaction divided by reactants raised to their coefficients. Now, if the value of K is greater than 1, then the products are favored, right, because our numerator is larger than our denominator, and that means we have a larger concentrations of our products than we do concentrations of our reactants. So if K is greater than 1, the products are favored, and that means that the forward reaction is more favorable than the reverse reaction. On the other hand, if K is less than 1, then the reactants are favored. We have more reactants than we have products, and that means that the reverse reaction is more favorable than the forward reaction. Now note here that by saying that one reaction is favored over the other, we are not saying that one of the reactions is occurring faster than the other. Because if we're actually at equilibrium, then both of these reactions, the forward and the reverse reaction, they have to be happening at the same rate. Because if the forward reaction occurs faster than the reverse reaction, that means that over time, our concentrations of reactants will go down and concentrations of products will go up. But that means we're not at equilibrium. So if we're at equilibrium, then the rates of those two reactions are the same. Now, note that each of the concentrations that we showed on the last slide in that equation is actually the ratio of the concentration of that chemical species to its concentration at standard state. Now, the standard state for solutes is 1 molar. The standard state for solids and pure liquids is the pure solid or pure liquid. And this means that pure liquids and pure solids are omitted from our equilibrium expression because the ratio would then be 1, and thus they wouldn't affect the value of K. Now, the concentration of a solvent is nearly 1, so it's usually omitted as well, although that is just an approximation. And the standard state for gases is 1 bar. So in that case, we generally would be writing it in terms of a pressure, so P sub whatever our reactant or product is, instead of a concentration of that reactant or product. Now, note that these conventions for standard states are completely arbitrary, but they allow us to create relatively small tables using the standard state and then calculate values at non-standard conditions. That is, we don't have to have a bunch of different tables for all the different possible conditions. We can instead have one table that occurs at standard states, and then we can perform some calculations to then determine what the values would be at non-standard states. So let's consider a generic reaction. In this case, the dissociation of an acid. So we've got HA dissociates into hydrogen ions and our conjugate base, the A-. And for that reaction, we have our equilibrium constant, which we're going to write K1 for the first deprotonation of our acid. So K1 is equal to the concentration of a hydrogen ion times the concentration of our conjugate base, A-, divided by the concentration of our protonated form, HA. Now, if we reverse the direction, then the value of the equilibrium constant is the reciprocal of the original value. That is, if we're protonating, we have our hydrogen ion plus our conjugate base, A-, which then react to give us HA, the protonated form. And for that reaction, we then have K1 prime, which is simply the concentration of HA divided by the concentration of H plus times the concentration of A-. And note that this fraction here is simply the inverse of the fraction up here, and that means that K1 prime is simply the inverse of K1. Now, if we add two reactions, then the new equilibrium constant is the product of the two individual values. So let's look at an example. If we have the deprotonation of acid A, so we've got HA deprotonating to H plus and A-, and then we have the protonation of base C, so we have H plus plus C react to give us CH plus. We've got our two equilibrium constant expressions here. K1 is equal to concentration of H plus times the concentration of A minus divided by the concentration of HA. K2 is the concentration of CH plus divided by the concentration of H plus times the concentration of C. Now, if we add these two reactions together, then we have HA plus C react to give us A minus plus CH plus. That is, we've got our protonated A, the proton comes off the A, it attaches to the C, so A is now unprotonated and the C is now protonated. And now, in this case, we've got K3, well, we're going to again take the concentrations of our products, so we've got the concentration of A minus times the concentration of CH plus, and then divide by the concentrations of our reactants, so divided by concentration of HA times the concentration of C. Now note that this fraction here, we can then split up into H plus times A minus divided by HA times CH plus divided by H plus times C. Note that really we're just multiplying by H plus over H plus, so we're multiplying by 1. And now, of course, this left fraction is then K1, and the right fraction is K2. So K3, our overall equilibrium constant, is simply K1 times K2. It's simply the products of our two equilibrium constants for those reactions that we added up to give us our overall reaction. Now, of course, you could do this for more than just two reactions, and this will hold for whatever set of adding reactions that you perform. So now let's turn to equilibrium and thermodynamics, and let's make a few definitions. The enthalpy change, which we'll symbolize as delta H, is the heat absorbed when the reaction takes place under constant pressure. Now, the standard enthalpy change, which is delta H naught, is the enthalpy change when all reactants and products are at standard state. Now, a negative delta H indicates that heat is being released and thus represents an exothermic reaction. On the other hand, a positive delta H indicates that heat is being absorbed and thus represents an endothermic reaction. Now, entropy, which will symbolize S, is a measure of the disorder of a substance. Now, entropy, which we'll symbolize with a capital S, is a measure of the disorder of a substance. And note that the entropy for a gas is much, much larger than the entropy for a liquid, which is a little bit larger than the entropy for a solid. Now note that a positive delta S, or change in entropy, represents an increase in entropy and thus an increase in the disorder of our system. Our system has gotten more chaotic. On the other hand, a negative delta S represents a decrease in entropy and thus a decrease in the disorder of our system, which means an increase in the order. Our system has become more ordered, and that's caused a lower entropy, right? A negative delta S. So something like assembling bricks together to form a wall is a negative change in entropy. The wall has a significantly lower change in entropy than a pile of bricks on the ground that are just scattered. On the other hand, if we break down our wall, we had a very highly ordered state, a nice brick wall, and now we just have a pile of bricks on the ground, so now we have, with this change, a positive delta S. So one way of thinking about this is, in general, it takes work for us to have a negative delta S. It's going to take some work to stack bricks together to form a nice orderly wall. On the other hand, it doesn't take much work to go the other way. So one way of thinking about this is that, in general, to get a negative delta S, we have to do some work. We have to put some energy into the system. That is, if we want to, say, stack bricks to form a wall, to change from a pile of bricks into a wall, we're going to have to do some work to get that process to go. It's not just going to spontaneously happen on its own. On the other hand, deconstructing a wall, turning a wall back into a pile of bricks, is relatively easy to do. You don't have to put in any work to get this done. Just maybe a little bit of activation energy in the form of, say, a big wrecking ball or a hurricane. That is, positive changes in entropy, positive delta S, is generally a spontaneous process. So systems that are at constant temperature and pressure, which is common under laboratory conditions because it's relatively easy to control the temperature and it's relatively easy to control the pressure by just leaving the vessel open to atmosphere. So systems at constant temperature and pressure have a tendency toward lower enthalpy and higher entropy. That is, negative delta H and positive delta S is favored at all temperatures. That is, there's a thermodynamic driving force pushing these reactions forward. On the other hand, positive delta H and negative delta S is disfavored at all temperatures. That is, there's a thermodynamic driving force pushing these reactions backwards. That is, there's a thermodynamic driving force pushing the reverse reactions forward. Another way of saying that is the reverse reaction is thermodynamically favored. It has a negative delta H and positive delta S, so that falls into this first category. Now, reactions that have the same sign on delta H and delta S have certain temperature regimes where they are favored and certain temperature regimes where they are disfavored. And then in between those two, there's a single temperature at which the forward and reverse reactions are neither favored nor disfavored. That is, we're at equilibrium. Now the Gibbs energy, also called the Gibbs free energy, which we symbolize delta G, is a measure of the amount of work available from a process under constant temperature and pressure. Now the Gibbs energy is defined as equal to the enthalpy H minus T times S, the temperature, times the entropy of our system. Which means that if we have a constant temperature, then delta G is equal to delta H minus T delta S. Now a process is thermodynamically favored if delta G is less than 0, if delta G is negative, and it's disfavored if delta G is greater than 0, that is, if delta G is positive. Okay, so here we have a table. Along the left side, we have our change in enthalpy. We have either a positive change in the enthalpy or a negative change in enthalpy, so delta H is positive or delta H is negative. And then along the top, we've got the change in entropy, whether it's positive or negative. Now, if we have a positive change in entropy and a positive change in enthalpy, then that positive change in entropy is thermodynamically favored, but the positive change in enthalpy is thermodynamically disfavored, which means it's going to depend on the magnitudes of delta S and delta H. So if the magnitude of delta H, so the absolute value of delta H, is greater than the absolute value of T delta S, then our Gibbs energy will be positive. That is, the reaction is disfavored. On the other hand, delta G will be negative if T delta S is larger, or the magnitude of T delta S is larger than the magnitude of delta H. That is, these processes are favorable at high temperatures and they're unfavorable at low temperatures. On the other hand, if we have a positive delta S and a negative delta H, now we have a delta G that is guaranteed to be negative at all temperatures, and this means that that reaction is favorable at all temperatures. Now if we have a negative delta S and a positive delta H, this means that our delta G has to be positive. It's got to be greater than 0 at all temperatures. In other words, no matter what the value of T is, delta G is positive. And that means that this reaction is unfavorable at all temperatures. But if we have a delta S, a change in entropy that is negative, and a change in enthalpy that is also negative, then we have some temperatures at which it's favorable and some temperatures at which it's not favorable. That is, delta G is positive, or greater than 0, if the magnitude of our enthalpy change is less than the magnitude of T delta S, or delta G is negative, favorable, if the magnitude of delta H is greater than the magnitude of T delta S. That is, such a reaction is favorable at low temperatures and unfavorable at high temperatures. All right, so now let's tie together our thermodynamics with our equilibrium expression. So the equilibrium constant K depends upon the value of delta G naught, the Gibbs energy at standard state, by this reaction, by this equation. K is equal to E raised to the negative delta G naught divided by RT. That is, the more negative delta G naught, then the larger the value of K. So remember that a negative delta G is spontaneous and a positive delta G is non-spontaneous. So if we have a negative delta G, then we have a favorable reaction, thermodynamically favorable reaction. That reaction will be spontaneous. That means that our value of K is greater than 1, and that means that the more negative delta G becomes, then the larger K becomes. The farther we're pushing our reaction towards our product. On the other hand, if delta G is positive, then that reaction is non-spontaneous. The reverse reaction will be spontaneous. And that means that if delta G is positive, then the value of our exponent here is negative, and the larger delta G becomes, then the smaller this side of the expression becomes, and thus the smaller our equilibrium constant becomes. The smaller our equilibrium constant, the more favored the reactants are, the less favored our products are. So you probably remember Le Chatelier's principle, which says that after a system that's initially at equilibrium is changed in some way, then the direction in which the system proceeds back to equilibrium is such that the change is partially offset. You'll never totally offset that change and get totally back to where you were, but you will partially offset that change. So let's look at an example. If we've got bromate plus 2 chromium ions plus 4 waters reacting to give us bromide plus dichromate and 8 hydrogen ions, then we've got our equilibrium expression given here. So we've got K is equal to the concentration of bromide raised to the first power times the concentration of dichromate times the concentration of hydrogen ion raised to the 8th power divided by the concentration of bromate times the concentration of chromium raised to the second power. Now the reaction quotient, which we symbolize Q, is similar to K, the equilibrium constant, but the reaction quotient is a measure of how close to equilibrium a system is. Now, the form of the equation is exactly the same as it was for K. It's just now with K, we had to be at equilibrium. With Q, we do not have to be at equilibrium. We can take any state of our system and compare it to the equilibrium state. So another way of saying that is that Q has the same form as K, but in K, these concentrations had to be the concentrations at equilibrium. In Q, they don't have to be the concentrations at equilibrium. Oh, we could be at equilibrium. They just have to be the concentrations at some time. So a Q equal to K means that our system is at equilibrium. The ratio of products to reactants we have at this moment is equal to the equilibrium ratio. On the other hand, Q greater than K means that the products dominate and the reverse reaction is favorable. That is, the ratio of concentration of products to concentration of reactants is higher than it is at equilibrium, or than it would be at equilibrium. On the other hand, if Q is less than K, then that means that the reactants dominate. Our ratio there is lower than K, and that means that our forward reaction will be favorable until we get that ratio to be equal to K. Now, the value of the equilibrium constant K depends upon the temperature. Remember that K is equal to E raised to the negative delta G naught divided by RT. That temperature there is in the denominator of our exponent. Now we can combine this top expression with our definition of delta G. Remember, delta G is equal to delta H minus T delta S. That's at constant temperature, of course. Now, if we combine those two and do some math, we eventually get that our value K, our equilibrium constant, is equal to E raised to the negative delta H naught divided by RT times E raised to the delta S naught divided by R. So now, the second term, this term here, is independent of the temperature, at least over a limited temperature range in which delta S naught is constant. The first term here increases with increasing temperature if delta H is greater than 0, that is if it's positive, and that term decreases if delta H is less than 0, if delta H is negative. That is, the value of our equilibrium constant K increases when temperature increases for endothermic reactions, and the value of K decreases when temperature increases for exothermic reactions. Now, these results are explained by Le Chatelier's principle if energy is considered to be a reactant or a product. That is, for endothermic reactions, we have energy plus our reactants react to give us products, or for exothermic reactions, we have reactants reacting to give us products plus energy. So for our endothermic reaction, if we increase the temperature, then we're effectively adding a reactant. That means that we're going to shift the equilibrium to the right, or if we decrease the temperature, we're removing energy, so we're going to shift our equilibrium back to the left. On the other hand, for exothermic reactions, if we increase the temperature, we're adding effectively a product. We're going to shift equilibrium to the left. If we lower the temperature, we're effectively removing a product. We're going to shift equilibrium to the right. Now, note that thermodynamics predicts only the direction in which a process will proceed spontaneously. It does not predict the speed with which it does so. Remember that kinetics predicts the rate of reaction. So thermodynamics only tells the direction of that spontaneous change. That doesn't actually mean that the reaction will occur at any reasonable rate. Remember that diamonds are thermodynamically unfavorable at room temperature and pressure. The thermodynamically favorable form of carbon at room temperature and pressure is graphite, what you have in pencils. But the reaction rate turning diamonds into graphite is incredibly low at room temperature and pressure. So your diamond ring is not going to turn into a graphite ring anytime soon. So now let's look at solubility product. The solubility product, which we symbolize KSP, is the equilibrium constant for a dissolution process, for dissolving something. For example, let's look at mercury 1 chloride. We have Hg2Cl2 in the solid phase, dissolves to give us mercury 1 plus chloride, and both of those are aqueous. Now the KSP expression there is the concentration of mercury 1 times the square of the concentration of chloride ion. Now remember, we're dividing by the concentration of our solid, but the solids are always given a concentration of 1 effectively, so we just ignore that. And we happen to know that the KSP here is 1.2 times 10 to the minus 18 at standard temperature. So a solution containing excess undissolved solid is what we call saturated. That is, we can't get any more of our solid to dissolve. Now, we can find the concentration of one of our ions given the concentration of the other ion and the value of our equilibrium constant, our KSP. So if the concentration of chloride ion is equal to 0.10 molar, then we can rearrange our KSP expression for mercury 1 ion, and that gives us 1.2 times 10 to the minus 18 divided by 0.10 squared, which gives us 1.2 times 10 to the minus 16 molar. So our concentration of mercury is so very low because we have a very, very small KSP. That is, mercury chloride, mercury 1 chloride, is not very soluble in water. So if we have any substantial concentration of chloride ions, we're not going to have very much mercury 1 ion in solution. Now, things are somewhat more complicated than this if either of the ions undergoes any other reactions in solution, or if the two ions form an ion pair. So what's an ion pair? An ion pair is a closely associated pair of ions that behaves as one species in solution instead of two separated ions. For example, let's examine the solubility of calcium sulfate. We've got our calcium sulfate solid, dissolves to give us aqueous calcium ions and sulfate ions, where the KSP there has a value of 2.4 times 10 to the minus 5. Now, if we have a saturated solution of calcium sulfate and we add another solute that produces additional calcium ions, then the concentration of sulfate ions must decrease. Now, this effect is called the common ion effect. That is, a salt will be less soluble if one of its constituent ions is already present in the solution. Now, note that the common ion effect is simply a specific case of Le Chatelier's principle. So now suppose we have a solution containing lead 2 ions and mercury 1 ions at a concentration of 0.010 molar each, and we wish to separate those two ions from one another. So we want to know, can we precipitate 99.990% of the mercury 1 using iodide before we precipitate any lead? Well, we can start by writing out our solubility expressions. We've got lead iodide dissolving to give us lead ions and iodide ions. We've got our KSP value there is 7.9 times 10 to the minus 9. We've got our mercury 1 iodide reacting to give us mercury 1 ions and iodide, and the value of our KSP here is 4.6 times 10 to the minus 29. So this is only going to work because the values of our KSPs are so very different. We've got 20 orders of magnitude between our two values for KSP. So to precipitate 99.990% of our mercury 1 ions, then we must reduce the mercury 1 ion concentration to 0.010% of its original concentration. So 0.010% times 0.010 molar is 0.00010 times 0.010 molar, or 1 times 10 to the minus 6 molar. So that's the concentration that we have to get our mercury ions down to without precipitating any of our lead. So now we can determine the iodide concentration that is necessary to reduce our mercury ion concentration to 1.0 times 10 to the minus 6 molar. So we've got our KSP expression here. We know that the value of KSP is 4.6 times 10 to the minus 29. We can solve that for concentration of iodide. So we get concentration of iodide is equal to the square root of our KSP divided by a concentration of mercury 1 ions, which when we plug in our values, then gives us 6.8 times 10 to the minus 12 molar. So that's the concentration of iodide that we need to precipitate out our 99.990% of our mercury ions. So now we can go ahead and determine whether this concentration of iodide will precipitate any of our lead iodide. So we write out our lead iodide KSP expression. We know that the value of KSP is equal to 7.9 times 10 to the minus 9. We can write out our reaction quotient. Q is equal to concentration of lead ions times concentration of iodide ions squared. And then when we plug in our values, concentration of lead was 0.010, concentration of iodide, which we found to be 6.8 times 10 to the minus 12. That then gives us a value of 4.6 times 10 to the minus 25. Now that value, 4.6 times 10 to the minus 25, is much less than 7.9 times 10 to the minus 9, which means Q is less than KSP, and that means that we will not yet have precipitated any of our lead. Now, we could have gone about this problem differently. We could instead have calculated the concentration of iodide necessary to precipitate any lead iodide. So let's go ahead and do that. We've got our lead iodide dissolution process. We've got our value of KSP equal to 7.9 times 10 to the minus 9. When we solve this for the concentration of iodide, we then get a concentration of iodide of 8.9 times 10 to the minus 4 molar. Now, this value is much larger than the iodide concentration that was necessary to precipitate almost all of our mercury, which means we shouldn't be precipitating any of our lead by the time we've gotten virtually all of our mercury out. Now, note that this is just in theory. We might co-precipitate some lead with the mercury, with the lead ions adsorbed on the surface of our mercury iodide crystals, or occupying some of the lattice sites. So the theory tells us one thing, the reality might be slightly different. We might get a little bit of lead that precipitates out. So let's look at complex formation. When an anion X- precipitates a metal M+, then we often see that a large concentration of X- causes solid Mx to dissolve. So this increased solubility is due to the formation of complex ions, such as Mx2-. That is, we've taken an Mx, something that was precipitated out, and we've now added to it another anion. So this complex ion is an ion that's composed of two or more simple ions bonded to one another. Now in complex ions such as these, where we have a lead-2 bonded with varying numbers of iodides, so we've got one iodide to form PBI+, three iodides to form PBI3-, four iodides to form PBI4-2-, and so on. These iodides are called the ligand of the lead ion. Now the ligand, or what we call the complexing agent, is any atom or group of atoms that is attached to the species of interest. In this case, our species of interest is the lead, so our ligand is the iodide. Now remember that a Lewis acid accepts a pair of electrons from the Lewis base. So in this case, the lead is acting as our Lewis acid. And the Lewis base donates a pair of electrons to the Lewis acid, so our iodide is acting as our Lewis base. Now, an adduct, or a coordination complex, is the product of the reaction between a Lewis acid and a Lewis base. So in this example then, the PBI+, the PBI3-, and the PBI4-2- are our adduct, or our coordination complexes. So a coordination covalent bond is the bond between a Lewis acid and a Lewis base. That bond between the lead and the various iodides. Now let's examine the solubility of lead-2 iodide. So we've got our lead-2 iodide solid dissolving to give us lead-2 and 2 iodide ion. We've got our KSP expression here, and the value of KSP is equal to 7.9 times 10 to the minus 9. Now, if this were the only relevant reaction, then the solubility of lead-2 would always be low in the presence of excess iodide. But at high iodide concentration, the lead-2 becomes soluble again, because it's starting to form these complexes. Now, when we examine the complex ion formation, we have our lead-2 ion reacting with some number of iodides. We have one iodide, we have two iodides, three iodides, four iodides, and that gives us then some lead iodide complex in these three cases, or our lead iodide just happens to be in the aqueous phase in this case. So we have our equilibrium reactions here, and we can write equivalent equilibrium expressions. So we've got K1 is equal to the concentration of products, PBI+, divided by concentration of reactants, PB2+ times I-. The value here is 1.0 times 10 to the 2, so this one is highly favored. Then we've got beta-2 is equal to PBI2 concentration divided by our lead-2 concentration times the square of our iodide concentration. The value there is 1.4 times 10 to the 3, so that's even bigger than the first one. Beta-3 is 8.3 times 10 to the 3, so that's even larger. Beta-4 is equal to 3.0 times 10 to the 4, so that's even larger. Now note that the stepwise formation constants, K sub I, so K1, K2, K3, K4, in this case, are defined as M plus X goes to Mx, well that's K1, and then Mx plus X goes to Mx2, that's K2, and so on. So we have Mx, n minus 1, plus another x, gives us Mxn for Kn. So on the last slide where we had beta 1, beta 2, beta 3, that was for the overall reaction. So when we went to the second one, that's beta 2, because beta 2 is equal to K1 times K2. That is, the cumulative formation constants, or the overall formation constants, are defined like so, where we have m plus 2x, this is beta 2, that gives us then mx2, so m plus n, some number n of x, gives us mxn, that would then be beta n. So note here that beta 2 is simply K1 times K2, beta n is K1 times K2 times K3, and so on up to Kn. So again, the cumulative formation constant and the stepwise formation constants are related like so. Beta n is equal to K1 times K2 times and so on up to Kn. So at low iodide concentration, then the solubility of lead ions is governed by the precipitation reaction. That is, the formation from our lead ions and our iodide ions of our solid lead iodide. And the value of Ksp there is 7.9 times 10 to the minus 9. On the other hand, at high iodide concentration, the solubility of lead 2 is governed instead by the complexation reactions because Le Chatelier's principle then drives those reactions to the right. That is, when we have a very high iodide concentration here, we have large concentrations of one of our reactants. Le Chatelier's principle is going to push those reactions to the right to form our complexes. And that then gives us these high values that we see over here for our formation constant. Note that if the system is at chemical equilibrium, then all the relevant equilibria are satisfied simultaneously. That is, the lead 2 concentration that satisfies the dissolution equilibrium must also be the same value as the concentration of lead that satisfies the complexation equilibria. And this is, of course, because the concentration of lead can't be one value for one reaction and a different value for a different reaction. The concentration of lead in some beaker is that concentration. So that same value must satisfy all of these equilibria conditions. So suppose we want to find the concentration of our complexes. Concentration of PBI plus, concentration of PBI2 in the aqueous phase, not the solid, concentration of PBI3 minus, and the concentration of PBI4 2 minus. Now let's say that in our solution it's saturated with our lead iodide, got plenty of our solid lead iodide around, and it contains a dissolved iodide concentration that is 0.0010 molar. Now we can find our concentration of lead ion in solution using the solubility. So when we rearrange the Ksp expression to get the lead 2 concentration, we get 7.9 times 10 to the minus 9 divided by our concentration of iodide squared, which then gives us a lead 2 concentration of 7.9 times 10 to the minus 3 molar. So now we know the concentration of lead ion in solution, and now we can go ahead and calculate the concentrations of our complexes. So we've got our formation reaction for our first complex where we've added just a single iodide. We've got our value for K1. We know that value is 1.0 times 10 to the 2. When we rearrange this expression to get the concentration of our complex, that's equal to the value of K1 times the concentration of lead, which we know now, times the concentration of iodide, which we also know. So when we plug in those values, 1.0 times 10 to the 2 times 7.9 times 10 to the minus 3 times 1.0 times 10 to the minus 3, we get a value of 7.9 times 10 to the minus 4 molar. Now note that this value is 10% of the concentration of our lead ion all by itself in solution. So it's substantial. The formation of our second complex, our uncharged lead iodide but dissolved in water in the aqueous phase, when we work that out using our beta 2, I'm going to skip the math here, but the value there is 1.1 times 10 to the minus 5 molar. For our third complex with 3 iodides bonded to the lead, we get a value of 6.6 times 10 to the minus 8 molar. And for our fourth complex, we get a value of 2.4 times 10 to the minus 4 molar. So note that each of these complexes have a successively smaller concentration, but overall we've still added a sizable amount to how much lead is in solution. It's over 10% of our concentration of lead all by itself. And that percentage is only going to go up as we increase the concentration of our complexing agent, in this case, our iodide. If we had more iodide in solution, then we'd have more of each of our complexes in solution. So remember that we have 3 different definitions in chemistry for what acids and bases are. We have the Arrhenius acid, which produces hydronium ion in water or H+ in water. We have an Arrhenius base, which produces hydroxide ions in water. We have a Bronsted-Lowry acid that acts as a proton donor. We have a Bronsted-Lowry base, which acts as a proton acceptor. And we have a Lewis acid, a Lewis base. The Lewis acid acts as an electron pair acceptor. The Lewis base acts as an electron pair donor. So the Arrhenius acid discusses what the acid or base does when dissolved in water. The Bronsted-Lowry acid or base discusses how that species reacts with a hydrogen ion. The Lewis acid or base discusses how that species reacts with electrons. Now note that the Arrhenius definition requires us to be working in aqueous solution. So if we're working in some non-aqueous solution, then the Arrhenius definition doesn't apply. The Bronsted-Lowry definition frees us to work in other solvents and also to work in the gas phase. Now, all Arrhenius acids are, by definition, Bronsted-Lowry acids, and all Bronsted-Lowry acids are, by definition, Lewis acids, but the reverse is not true. That is, not all Lewis acids are Bronsted-Lowry acids, although some of them are, and not all Bronsted-Lowry acids are Arrhenius acids, although some of them are. Now, the same is true for bases. All Arrhenius bases are Bronsted-Lowry bases, and all Bronsted-Lowry bases are Lewis bases, but the reverse is not true. So not all Lewis bases are Bronsted-Lowry bases, and not all Bronsted-Lowry bases are Arrhenius bases. Now, from now on, that is, in this class and in the book, the term acid and the term base refer to Bronsted-Lowry acids and bases. In other words, in an acid-base reaction, a proton is exchanged. If we instead want to be discussing a Lewis acid or base, we'll call it a Lewis acid or a Lewis base. So if we just use the term acid or base, we're talking about a Bronsted-Lowry acid or base. That is, we're talking about some proton exchange reaction. Now, you should remember from general chemistry that a salt is defined as any ionic solid. Now, most salts that are composed of ions with a single positive or a single negative charge are strong electrolytes. That is, something like ammonium chloride dissociates into ammonium with a single positive charge, +1, and chloride with a single negative charge, -1. Now, the products of an acid-base reaction are also an acid and a base. That is, a conjugate acid-base pair is a reactant and a product of an acid-base reaction that are related by the gain or loss of a single hydrogen ion. Now, when a hydrogen ion is in water, it doesn't exist by itself. It instead forms complexes with water. That is, the hydrogen ion doesn't simply float around as a single proton, as a single H+ moving through solution. It instead forms complexes with the water. Now, the most common complex is hydronium H3O+, but even this forms very strong hydrogen bonds with other water molecules. For example, if we have HClO4 with a water, it's not really an HClO4 molecule and a water molecule that are bonded to each other. What that really means is we have a hydronium ion that is our cation, and we have a perchlorate anion. Now, when hydroxide is in water, it will also form complexes with water, such as H3O2-. That is, we've got our OH- and we've added a single water molecule, a single H2O. Now, water is what we call amphiprotic. That is, it can act as either an acid or a base. So water acts as an acid with methoxide. So we have H2O, or in this case I'm going to write it as HOH, plus our methoxide. That reacts to give us hydroxide, plus now our protonated form, which is methanol. On the other hand, water acts as a base with hydrogen bromide. So we've got our H2O plus hydrogen bromide. That reacts to give us our hydronium ion plus a bromide ion. Now, water undergoes self-ionization, which we also sometimes call auto-ionization or autoprotolysis, where we have one water molecule and another water molecule will react with one another to give us a hydronium ion and a hydroxide ion. Now, sometimes we write this hydronium instead as a hydrogen ion, and then we drop one of our water molecules, so we write that instead as a single water molecule dissociating into H+ and OH-. Now, what we mean there isn't really that a single water molecule is spontaneously dissociating into hydrogen ions and hydroxide ions. What we really mean is a second water molecule has come along and stolen one of the protons off of our first water molecule. So our second water molecule becomes a hydronium ion, and our first water molecule becomes a hydroxide ion. Now, other protic solvents, such as acetic acid, also undergo auto-ionization. So if we have two acetic acid molecules, one of them can have both of its oxygens protonated, and then the other one becomes acetate. So let's discuss pH. We give the auto-ionization constant for water a special symbol, Kw. Because this is a special reaction, it's going to be present in all of our aqueous solutions. So this reaction here, the auto-ionization of water, is special. So the value for K there is a special value, so we're calling it Kw. So the value of Kw is equal to 1.00 times 10 to the minus 14 at 25 degrees Celsius. So note that the value of Kw here changes with the temperature. So if we change our temperature away from 25 degrees Celsius, we'll have a different value for Kw. Now, in the past, you've probably seen the definition for pH, that pH is equal to negative log base 10 of the hydrogen ion concentration. Now this is actually just an approximation. The true definition uses the activity of the hydrogen ion, not the concentration here. Now chapter 7 will more clearly define the pH in terms of activity, so this approximation here, using the concentration instead of the activity, works reasonably well at low concentrations of hydrogen ion, but it fails at higher concentrations. That is, if we have a very low pH, then this approximation is going to break down. It's not going to give us the correct pH value. Now, remember that the pH, the pOH, and the pKW are all related. The pH plus pOH is equal to pKW. Now, pKW is equal to minus log base 10 of the KW, which is 14.00 at 25 degrees Celsius. Now, strong acids and bases completely dissociate in aqueous solution, or nearly so, near enough that we don't need to worry about it. So we have something like hydrochloric acid is a strong acid that dissociates virtually completely into hydrogen ions and chloride ions. Now, what we really mean here, again, isn't really hydrogen ions, it's really hydronium ions and the other proton-water complexes, but we're going to write it for simplicity as H+. Potassium hydroxide is a strong base, which means it dissociates virtually completely into potassium ions and hydroxide ions. Now, weak acids react with water to form hydronium and the conjugate base of the acid, A-. So HA plus H2O react to give us hydronium, H3O+, plus A-, our conjugate acid. And we've got some acid dissociation constant, Ka there. So we can also write this as HA dissociates into H+, plus A-, where we've basically just dropped the water out. We're assuming that this is occurring in water, so we're basically dropping it from the left and the right side. And then the value of our equilibrium constant, our acid dissociation constant, Ka, is equal to concentration of H plus times concentration of A minus divided by the concentration of HA. So again, this Ka is our acid dissociation constant, and since weak acids are only partially dissociated in water, that means the Ka must be small. The Ka for a strong acid would be very large, something much, much larger than 1, but a Ka for a weak acid is by definition something less than 1. Now, weak bases undergo base hydrolysis with water. So if we have our base and we add water to it, we get BH plus, the protonated form of our base, conjugate acid of our base, plus hydroxide. Now there we have Kb, our equilibrium constant for the base dissociation, is equal to the concentration of BH plus times the concentration of OH minus divided by the concentration of our base B. Now again, Kb is our base hydrolysis constant, and again, since weak bases are only partially protonated in water, that means that Kb is by definition small for a weak base. For a strong base, Kb would be very large, would be greater than 1, but for a weak base, Kb is less than 1. So let's look at carboxylic acid. Carboxylic acids are weak acids, and carboxylate anions are weak bases. That is, if we have something like acetic acid that dissociates into acetate and hydrogen ions, the Ka value there, the acid dissociation constant, is equal to 1.75 times 10 to the minus 5. So again, that value is less than 1. That means that acetic acid, this is basically vinegar, is a weak acid. Now, amines are weak bases. That is, ammonium ions are weak acids. So if we have something like methylamine, which we'll symbolize with a B, and we add water to it, we get methylammonium ion, symbolized as BH+, and we get hydroxide ion. The Kb there is equal to 4.47 times 10 to the minus 4. Now, metal cations typically act as weak acids by acid hydrolysis. That is, we have our metal M with some power N+, and we add water to it, and we get out MOH with some charge N-1, and that charge will be some positive value. And we also get out a proton, a hydrogen ion. Now, you should remember from general chemistry that polyprotic acids and bases are compounds that can donate or accept more than one proton. For example, if we look at oxalic acid, we have 2 hydrogen ions here that can be lost. We're going to lose this left one first, so we get oxalic acid dissociating into a hydrogen ion and monohydrogen oxalate. The Ka1 there is 5.37 times 10 to the minus 2. We can then take off our second hydrogen, the one on the right side, to give us another hydrogen ion and our oxalate ion. The Ka2 there is 5.42 times 10 to the minus 5. Now note here that Ka2 is smaller than Ka1. This is going to be true for all of our polyprotic acids and bases. As you remove more and more hydrogen ions from that species, it's going to become harder and harder to remove an additional hydrogen ion from that species. Because of course, that species is getting more and more charged, and thus it's becoming harder to pull off a positive charge from that species. So let's look at a polyprotic base. if we have phosphate and we add water, the phosphate can take one of the hydrogen ions off of the water, leaving us a hydroxide, and we get now monohydrogen phosphate. The Kb here, Kb1, is equal to 2.3 times 10 to the minus 2. If we then take that monohydrogen phosphate and we add another proton to it, we get dihydrogen phosphate and another hydroxide. Our Kb2 there is 1.60 times 10 to the minus 7. If we do this a third time, we then get our phosphoric acid, and that has a Kb3 of 1.42 times 10 to the minus 12. So again, we had 10 to the minus 2, 10 to the minus 7, 10 to the minus 12. So we're becoming less and less likely to add a proton to our base. That is, dihydrogen phosphate is not nearly as strong of a base as phosphate is. On the other hand, phosphoric acid is a much stronger acid than monohydrogen phosphate is. Now, recall that if we add two reactions, the new equilibrium constant is the product of the two individual values. So remember, we had this example where we had the dissociation of HA into H plus and A minus, and the protonation of C from H plus and C going to CH plus. When we add those two reactions together, we then have our equilibrium constant for that overall reaction was equal to the products of K1 times K2. So let's do something similar with the acid dissociation of an acid and the base hydrolysis of its conjugate base. So we have HA dissociating to give us H plus and A minus, and we have B plus H2O gives us BH plus OH minus. When we add those two together, we get HA plus B plus H2O react to yield H plus A minus plus BH plus OH minus. And we have our Ka, we've got our Kb, so when we multiply those two together, in our K3, that is the equilibrium constant for our overall expression there, is equal to Ka times Kb. But in this case, the conjugate base, A minus, is the same thing as our base, B. And that means that in our second reaction, we can replace the B with A minus. And so now we have A minus plus H2O react to yield HA plus OH minus. And then again, we can replace our B down here with A minus, and we can replace BH plus with HA. And now, when we add our two reactions together, now we have HA plus A minus plus H2O react to yield H plus A minus plus HA plus OH minus. And now you note that I've scratched out the A minus here and the A minus there and the HA on the left and the HA on the right. And now we simply have H2O reacts to yield H plus OH minus. And in our equilibrium constant expression, we have K3 is equal to the concentration of H plus times the concentration of A minus times the concentration of HA times the concentration of OH minus divided by the concentration of HA times the concentration of A minus. Well, these two cancel, those two cancel, and we're left with K3 is equal to concentration of H plus times the concentration of OH minus. But remember, K3 was also equal to Ka times Kb, and remember that the concentration of H plus times the concentration of OH minus is equal to Kw, the auto-ionization constant for water. And this means that for any acid-base conjugate pair, the value for Ka times Kb must be equal to Kw. So this now gives us a way of finding either Ka or Kb given the other one. We know the value of Kw, provided that we know the temperature, and if we know Ka, then we can find out Kb, which means that all we need to do now is tabulate the values for Ka, the acid dissociation constants for all of the acids that we know, and as long as we know the value of Kw, which we do, then we can generate the value for Kb. So we don't need to have a value of the acid dissociation constants for all of our acids, and a separate table for the Kb values for all of our bases. All we need to do is list the Ka values for the acids, and if you want to find the Kb value, you just need to look up the Ka value for its conjugate acid, do this calculation, and you'll know what your Kb value is. And that was chemical equilibrium.